Hello, everyone. Thanks for joining to this Zurich Instruments webinar on best practices in sensor characterization and control. I'm Kivanç Esat, an application scientist in Zurich Instruments. I'm honored today to also welcome Tomas Manzaneque from TU Delft. He is an assistant professor there. He actually received his position 2 weeks ago. So also please join me congratulating in his new position as well. So let's just dive into it. Let's start by looking at the typical sensor development workflow with these 4 stages. The first stage is characterizing the material itself, which can be a nanodevice, a thin film, a dielectric or a piezoelectric material, for example. And there are various methods to characterize their behavior. It can be optical spectroscopy, transport, or imaging, for instance. Designing the sensing element, it becomes the second. And to characterize its response to its environment requires a sweep of the parameter space. The impedance of such an element also can vary with the changing environmental conditions. Therefore, an impedance analyzer is also needed at this stage. In most cases, the best performance of the sensor is achieved with closed-loop control. Therefore, these control loops needs to be also implemented in addition. And typically, there are multiple of these loops run in parallel. But so far, this is actually an iterative process. Before gaining the confidence to be able to design the ASICs and then packaging the sensor itself, there are many of these iterations needed. And our instruments can help you at each of these stages in different ways. And today we will be focusing on the sensor design and characterization and the sensor control itself. So maybe first start with looking into how to recover a sensor's response actually. So what a sensor does, in its essence, it transduces the information about its environment into electric signals. So, and the key here is to preserve the information in such signals. So the sensor can be working with various forms. It can be a mechanical sensor, for instance, looking for inertia, sensing inertia or strain. It can be probing environmental properties of gas phase, for example, or a material properties itself, the phase of it, or conductivity. And these things all rely on different physical principles, so we have different methods to probe, of course, optical, inertial, or transfer, which few I mentioned already. But in the end, we are interested to study the electric signals that the sensor in the end provides. So today we have 2 parts actually. In the first part, I will be looking into why such a signal recovery is necessary for sensor characterization and why a lock-in amplifier is beneficial there, and where do a modern lock-in amplifier makes really a difference. And then Tomas will take up for the next part, where he will be focusing on the resonant mass sensors and describing his research there from working principles of sensors to how to achieve femtogram sensitivity. And of course, characterization, stability, and resolution is essential at that point. And he will be also talking about the open loop and closed loop behavior of such devices and the differences in their behavior in between. So in Zurich Instruments, our mission is to provide best-in-class dynamic signal instruments for advanced R&D labs. But how do we do that? We take, when we develop an instrument, we look at the market for the hardware, gather the one that acquires enough speed or the good sensitivity, the low noise floor, etc. But this is in the end what everybody does, our customers as well. And where we differentiate ourselves is actually putting together such a hardware with the software, with providing efficient workflows. And this is where our customers actually save time and do things they cannot do otherwise, or they cannot do as fast. And the best part is we upgrade this software quite often, and the value, basically the functionality also increases over time. So the value of the instrument also increases over time. By putting these 2 aspects, we develop instruments such as lock-in amplifiers and impedance analyzers, which we'll be looking into most of the time today. We also provide other instruments, of course, like boxcar averages and quantum control systems. So let's look at a very typical system. In this case, it's a nanomechanical mass spectrometer. Here we have the resonator itself that is actuated from the signal coming from the lock-in amplifier itself. And we depict its motion by a laser reflected on its surface that is then impinging on this photodetector there, and then we use the lock-in amplifier to probe this signal. And in the end, what is needed is to characterize how the cantilever moves, of course, so therefore characterizing its different eigenmodes. Here we actually have a frequency response analysis of various eigenmodes as well. We will be looking into this a bit more detail, but in the end, this is a typical experiment. And we need to understand what happens when, for example, some particles deposited on this actuator. So what kind of signal then we are talking about in the end in such a situation? So we have a parameter variation, so landed particles on the cantilever itself, and this then leads to a time-dependent signal. So we need to look at multiple parameters. This can be the phase delay in time, for example, the duration of a certain period, or the amplitude change. And the key to be able to capture this information is to optimize the signal-to-noise ratio to be able to capture all these components. So therefore, the suppressing noise is essential. To be able to do this, we first need to characterize the noise floor of the environment. And typical noise floor here is the white noise here that shows the baseline of the noise. We have various noise spikes coming from different sources, and we have the 1/f noise that picks up at higher frequencies. So if you would be doing the measurement in this noise regime, of course, then the signal to noise ratio gets reduced. So what we then do is to modulate the signal to higher frequencies, or the regime where the noise floor is lower, and this is where we can also then benefit from the lock-in the most, because it can measure the signals at the frequency that we are modulating the device. And in this case, we basically modulate the sensor's drive signal. And in this picture here, in time versus the amplitude, you can see how noise is different for different frequencies. And this is because of this noise floor. And how a lock-in amplifier in the end works. It's a two-step process. We have the signal coming in that is then mixed with a reference signal at two phase here at 0 and 90 degrees. And these two signals then low-pass filtered, which provides out the X and Y components. So in the complex domain. And from this, we can then calculate the amplitude and the phase of this signal. But this is not the whole story. Since the instruments we also provide work in the digital domain, you can actually make this multiple of these blocks running together. So we can have multiple demodulators and oscillators to be able to characterize various frequencies at the same time. And in addition, the signals here are already in digital domain. It's possible to add additional time and frequency domain tools there as well. And on top, feedback controllers to control the entire system can be built on top of that. So I like to focus a little bit now on the low-pass filter side, because this is a key element of the lock-in detection. And the low-pass filter has various parameters to adjust. One is its bandwidth, here depicted by F. It is inversely proportional with the time constant. And here we see its time domain response and the frequency domain response. With a broad filter, we essentially pick up larger noise. In this case, for example, in this example here, we have the amplitude and time. We have certain features, but we can clearly see them, but there is also a lot of noise there. By having a narrower filter, we can clean this noise quite a bit. But then you can ask the question, yeah, why we don't go with always narrow filter? Unfortunately, this is not the case, because in this scenario, for instance, if you have a narrower filter, the features are there, but they are skewed. And this is because the time constant, which I mentioned earlier, is higher. So the step response of this filter gets lower. So then the bottom line is, for a measurement, we want to keep the filter bandwidth as narrow as possible, but it should still support all the signal components that we need. The next parameter is the filter order. That's the N here. That is essentially how many filters we cascade, and this affects how steep such a filter is. If you look at the frequency response here, you see that the dark blue is the one with the filter 1, order 1, and the other one, the lighter it gets, it essentially gets steeper because the filter order increases. How it reflects itself in a signal, here we have a third order filter we see the features, but there's an additional modulation on top. This order filter cannot clean this up. To solve this problem, we can increase the order here, and you see the features are there. We even actually capture a feature that we couldn't resolve before. So in the end, the filter order also needs to be low, because when you increase the order, it also increases the time response or the step response of it, but it needs to be high enough then to suppress all superior signals. So in a nutshell, these parameters that you need to look for when you are setting up a locking amplifier. So, but when you actually look in the market when you're searching for an instrument to recover your sensor response, it's important, of course, to choose the right tool. One parameter that you can look at, of course, the input bandwidth, but that's not the whole story. The minimum maximum time constant that the instrument provides, its input noise or dynamic reserve are the important parameters that you can look into as well. In addition to such specs, a modern locking amplifier, of course, can offer more. This could be the integrated tool set for the time and frequency domain tools, which we will look into in a second. Of course, the number of demodulators or the ability to probe multiple frequencies simultaneously is important. And in addition, can it actually provide feedback controls, PIDs, PLLs essentially, and how this is actually put together in a software. If you have questions, of course, please contact us. We are always happy to help for you to choose the right tool. So let's look at the time and frequency domain tools first. Here we have the frequency response analysis of a sensor. Essentially, such a measurement allows us to determine and then drive the sensor at the optimum conditions. And then, but frequency sweep is not the only thing. Of course, we need to sweep other parameters. For instance, here we sweep a gain of a resonator, and at higher gains, we see the behavior of the resonator becomes nonlinear. And then this is how we can also determine the sweet spot where we need to drive the resonator itself. In addition, the time response of such a resonator, for instance, when we have a step change in its environment, how fast it settles. In this case, the blue curve depicts a sensor that is underdamped, so it doesn't settle that fast. And this is not the case for the other ones. As the last example, let's look at the impedance analysis. So, for instance, a MEMS device which is capacitively coupled to its environment. When we have a bias change, for instance, there you see a very fast steps in the signal. For instance, here we have the capacitance that changes, and here how the impedance changes as well. And this happens in very short time scale. So we are talking about only a few microseconds. And this measurement is done on a MEMS device with our MFAA impedance analyzer, which enables this high precision and also fast measurements. So just to summarize, the tools we looked into is the frequency response analysis, the parameter sweep to determine the sensor's response at different parameters, step response measurements in time, and then the impedance analysis. And very important that all these tools can run in the same box, of course, and they can run simultaneously as well. So you can do this characterization at the same time and capture the key information about the sensor. So far we looked at the open loop behavior. So the drive signal was steady. What is the problem there? Here I'm showing the proximity sensor. When we perturb the sensor, of course, its behavior changes. We look at the amplitude and phase of its response. But once the sensor settles, it doesn't settle to the same spot. So it actually settles to an arbitrary state. And this makes us very hard then to characterize its behavior. And also, if you look at the response time, we then only rely on how fast the sensor actually decays itself to a steady state. And to fasten this process, the solution is going for closed loop control. And this is done by feedback control loops. In addition to the locking amplifier, then where we measure the signal, we then have a feedback controller that then updates the signal that we drive, so we are always driving the sensor at the right conditions. And a typical workflow is the lock-in amplifier measures here, so we have then the input signal at the controller, and we need to compare this signal with a given set point, which then provides us with the error signal. This error signal then gets processed by the PID controller itself, that provides us the signal in the end that will minimizes this error. So depending on the system, you might need to look at different signals to be able to control. So in the digital implementation, you can select these different signals quite straightforward way. For instance, a demodulator signal can be, you can actually get a signal from another PID controller, for example, to cascade these controllers, depending on the situation, of course. And then on the other side, the output can be controlling an amplitude, a frequency, or phase offset, for example. Here, a typical example, the blue curve is the phase, and the orange curve is the amplitude. Here, at this point, a phase lock loop kicks in to actually stabilize the phase, and you can see the difference is very clear in the sensor's response. But the amplitude is still free running at this point, and to be able to stabilize that, we need another loop that runs in parallel. Once it's closed, then we have both amplitude and phase stable. So this is then called amplitude gain control, actually. And this is pretty often used in such systems as well, which this is the system which I started initially. I don't need to repeat the scheme, but in the end, we start by characterizing this cantilever's eigenmodes, and then we can close control loops to be able to track these eigenmodes at its resonance frequency on each of them simultaneously. And this plot actually shows us how much this resonance frequency drifts when a particle gets deposited on the cantilever surface. And this shift is essentially a function of the edit mass. And from there, we can depict the mass distribution of many particles landing on the cantilever. And in this picture, you can see these dots essentially are the particles on the cantilever. This is the point actually I will stop, and I hope this will be a nice transition as well for Tomas to pick up from where I finished. Tomas, please, you can also start the screen share.
Thank you, Kivanç, for the introduction, and also for inviting me to participate today in this nice webinar. So as Kivanç described, I will be talking about the work we have done in my department on the limits of detection of resonant mass sensors in the last years. So I would like to start by the fundamentals, by the beginning, how a resonant mass sensor works. Well, a resonator or a mechanical resonator is a suspended structure, as you can see here, that presents a resonance, actually many resonances, but we will focus on one for sensing. And then we can model it as a mass spring damper system if it's fully linear. Sorry, 1 second. And then when we have a mass or a particle attached to the device, we will see an increase in the total mass of the device, and then a decrease in the resonance frequency. So we can monitor resonance frequency, and we can actually relate this decrease that we see with the added mass in the resonator. So if we look at the literature, we can see that these devices can get really sensitive. So devices in the microscale can reach the attogram level. And at the nanoscale, people have demonstrated the septogram level, sorry. And then by harnessing the vibrations of a single thermonanotube, the joctogram level has been achieved. And this corresponds to the mass of a single proton. So you can see already the trend here that higher miniaturization means a lower mass resolution. But why is this? And especially how, where does this limit come from? This is what I want to discuss now. So if we want to detect the resonance frequency of a resonator, we need to interrogate it. So we apply a force, and then we obtain its displacement. Right? But when we do this process experimentally, we're actually adding noise because the signal that we apply will contain some noise, and also the displacement that we read will contain some noise from the instrumentation that we are using. So due to this noise added in our signal, we will have some uncertainty in the determination of the resonance frequency. In addition, we can have fluctuations in the resonance frequency that we cannot predict. For instance, if there are drifts or fluctuations in the temperature of the room or in the pressure or in the environment of the resonator, this is something that will create some shifts that we cannot predict and don't correspond to the mass that we are trying to detect. So as a result of all these processes, we will have some error in the frequency, and this will set the minimum frequency or the minimum variation in the resonance frequency that we can determine with our sensor. And then, of course, this minimal resonance frequency change will determine what is the minimum mass change that we can measure also. So let's see it in a more quantitative way. So if we want to obtain that mass resolution or minimum mass change that we can detect, that we call delta M, we just have to multiply the inverse of the responsivity, which is just the derivative of the resonance frequency with respect to the effective mass of the resonator, by the minimum frequency resolution, or sorry, the minimum frequency shift that we can detect, or frequency resolution that I just described in the previous slide. Then to obtain this responsivity, well, it is quite easy if we just take the expression for the resonance frequency in a mechanical resonator, and we just do this derivative. Then we plug it in this equation, and we'll see that the minimum mass that we can detect is twice the mass of the resonator by the frequency resolution, or actually a normalized frequency resolution. So in this equation, you can see why miniaturization helps to reduce the mass resolution, is because we have the mass of the resonator here. And then we have this other term, the normalized frequency resolution, which is a bit more difficult to analyze and also more interesting. To characterize, or actually to measure this normalized frequency resolution, we use the Allen deviation, which is a statistical tool. And let me introduce what is that. What is the Allen deviation? So imagine you have, in principle, any variable, any normal variable. If you want to see what is the dispersion of it, you use the standard deviation, which just takes each point in a data series and compares it to the average and squares this difference, and then it calculates the average of all these differences. And this gives you, the standard deviation gives you a measurement of the dispersion of that signal. However, when we deal with not with just any signal, but specifically with frequency signals over time, as we can see here, this Y represents the normalized frequency readings, we use the Allen deviation. And the difference in the calculation is that instead of comparing each readout value with the average, we do it with the previous measured value. And again, we do the square value and the average of them. And this will give us a measurement of the dispersion of these normalized frequency values that can correspond to readings of the resonance frequency of a resonator, for instance. But this method is general for any frequency signal. And as you can see here, there is an important parameter, which is the time separation between measurements, or this is the inverse of the sampling frequency, that we call gate time or average time. That actually is a measure of how long do we take to measure each of these points. This is why it's called also integration time. And our Allen deviation will be influenced by this gate time that we use in the measurement. Typically, when we have longer Allen deviations, due to this averaging, this integration will have, when we have longer gate times, we will have smaller Allen deviations, but this is not always the case. It depends on the type of noise. But then you might be asking, why do we use Allen deviation and not standard deviation for frequency measurements? And the reason is in convergence, statistical convergence. Because when we measure the dispersion, we want that if we measure many samples, so this n tends to infinity, this dispersion value tends to a finite value. So when we have frequency data and we use the standard deviation, this condition is not met, especially if we have flicker noise. There is a lot of mathematical details involved to reach this conclusion. But the take-home message here is that in the particular case of frequencies, we use the Allen deviation, which is just a modified version of the standard deviation. And then I would like to discuss on measurement schemes for resonant sensors. So the most, let's say, easy one, or the most immediate one, is to use an open loop scheme in which you interrogate the resonator by applying a force with an actuator, and you do it at a signal at the resonance frequency. Then with a lock-in, as Kivanç showed in his presentation, you can measure the phase of the response with respect to the actuation signal, and you can do this in real time. So if we do that, we know what is the phase curve of a resonator versus frequency, and we know that this slope is known, right? So if we see changes in the phase, we can relate these changes in the phase with changes in the resonance frequency, because we know this slope. But of course, this is only true for a very small frequency, for very small frequency variations. But if we have a large mass added, or if the resonance frequency is presenting drift and due to temperature changes, and then the resonance frequency changes significantly, then we are in a situation like this in which we no longer know what is the slope of the curve here. So we need to update our resonance frequency, our actuation frequency back to the new resonance frequency. So we need a system to do this continuously, to update the actuation frequency continuously. And this is exactly a closed loop system, which is the second method for interrogation. So in this case, we also have a resonator here. Now I included an example of a particular resonator. We also have an actuator, and we also have a detector or a readout system that in this case is a laser Doppler vibrometer. And then to apply the signal, the force signal, we use a voltage control oscillator, which is provided by our digital lock-in. And well, this is a block that provides a sinusoidal signal whose frequency is variable and can be controlled by this terminal here. Then we have our lock-in that detects the phase of the displacement with respect to the force. And then we set a PI controller that takes these phase values and calculates the new frequency of actuation, so we are continuously at resonance. So if we properly select these proportional and integral constants, and there are some publications that describe how to select them, we'll have a properly designed phase lock loop, and then this will continuously track the resonance frequency of the resonator, and then we have a sensor with a very large measurement range, right? Because this can still measure even if the resonance frequency shift is large. So then once we have a proper system like this, a closed loop system, we wonder what is the minimum mass resolution that we can have with that. And let's say we disregard any type of noise present in the measurement system. What is that limit that we call ultimate limit when there is no noise in our measurement? And this is given by the thermomechanical noise of the resonator, which is a noise that is present there just because the resonator has certain temperature, and the particles or the atoms forming the resonator have some thermal energy, some agitation, and that will excite the resonance, right? So we can model this quite easily by considering a random force on top of the force that we apply to interrogate the resonator. And this random force has a wide spectrum and Gaussian distribution, and the fluctuation dissipation theorem tells us exactly what is the power spectral density of that, what is the amount of that wide distributed force. And this depends just on the temperature and on the parameters of the resonator, namely the stiffness, resonance frequency, and quality factor. So we can do some math and introduce this wide spectrum force into the transfer function of our resonator, and also include the closed loop system, and we can obtain what is the Allen deviation that we expect from that from this thermomechanical noise. And we see that this is the limit, which is just determined by the temperature and some properties of the resonator, and this is the amplitude at which we drive the resonator. And then we can easily translate this Allen deviation into a mass resolution by just multiplying multiplying by twice the effective mass of the resonator. But then the question is, well, how to determine all the parameters in this equation, in this function? Well, I'll go through all of them quickly. So first, if we want to determine the resonance frequency and quality factor, well, I'm sure most of you know, you just can make a frequency shift, then you measure the amplitude and the phase, and you can fit these curves to a Lorentzian, and then you can easily obtain the resonance frequency and quality factor. But what about the stiffness? So if you excite your resonator with an external piezoelectric, for instance, you don't have information about the stiffness because you don't know what is the force that the piezoelectric is exerting on the resonator. So we can do a measurement in which we don't apply any force. So this is a measurement in which there is no actuation. Just this is a measurement of the displacement of the device when it's resting, and we will see that the power spectral density of that displacement is concentrated also around the resonance, and we can fit this power spectral density to a Lorentzian function also, and this will give us what is the stiffness, the effective stiffness, and effective mass of the resonator. And then finally, we have the actuation amplitude here. This means what is the displacement of the resonator, the harmonic displacement that we set in order to interrogate it. So in principle, we see that it's in the denominator. So we should increase this displacement as much as possible, because then we will have a smaller Allen deviation. But of course, there will be a limit for that. And to know that limit, what we can do is to do frequency sweeps for different actuation powers. And we'll see that the resonance starts to bend either to the left or to the right. And we call this behavior, this is a nonlinear behavior that we call Duffin behavior. And we know that when this starts to happen, the Allen deviation will be much bigger than this due to the nonlinear phenomenon. So we need to stay away from this part. Then if we want to minimize the Allen deviation, what we do is excite the resonator at the highest displacement possible before reaching that nonlinear regime, just below the onset of these nonlinearities. So we can have all the parameters that we need. Now we can estimate what is, or we can calculate what is our ultimate limit. And yeah, to illustrate this process, I will show the data for these devices that we built here in-house at TU Delft. And they consist of microfluidic channel. As you can see here, this is the microfluidic channel. There is an inlet and an outlet, and part of the channel is suspended. So it forms a resonator, a cantilever, in fact. You can see a zoom in here. And this is a cross-section of the suspended part, where you can see that it's hollow inside. So in this device, yeah, we can make fluid circulate through the channel, and we can put particles in this fluid. And this is particularly interesting for particles of biological interest that need to be in water solution, like bacteria. And then we can detect the mass of such particles. And the beauty of this device is that the resonator can be vibrating in a vacuum environment with a high quality factor in the order of more than 10,000, while the particles are still in their native environment in liquid. So we did this analysis of the ultimate thermomechanical limit for this device, and we could estimate what is the minimum Allen deviation that we can obtain with them for the empty condition, but also when the channel is filled with water. And it is a bit different because the effective mass of the resonator is changing due to the water. And as I said, we can just translate this Allen deviation into a resolution of mass by just multiplying by twice the effective mass of the resonator. And we can see that for a water-filled resonator like this, we can reach the attogram level of resolution. However, as I said, this is just an idealized case. So this is just when we don't have any other source of noise, just the thermomechanical noise. But then, of course, we want to know if our resonator with the measurement system that we have in the lab can actually reach these levels. So for that, we implemented a whole system in which we have a resonator like the one I showed in the previous slide, and it's excited by a piezoelectric. And then we measure the displacement with a laser Doppler vibrometer. And then we have our Zurich Instruments to provide a reading of the phase through a lock-in, and then implement a whole phase lock loop as I described before. Then this system gives us a reading of the resonance frequency versus the time. And from this, we can calculate the real Allen deviation, the actual Allen deviation of our resonator and our measurement system. Again, we did that for our resonators, and we found these real limits. You can see here in blue, they correspond to the measured Allen deviation versus the gate time. And then in red, they are translated into mass resolution. And we see that our real limits are more in the femtogram level. And we can also conclude that if we invest more in our measurement system, or if we have a measurement system that provides less noise, such as a different way of determining the displacement, we can actually improve our limits of detection by 2 orders of magnitude. So this is quite valuable information. And of course, even though we know the limits, we also wanted to try that our resonator can actually detect particles. So we implemented the whole PLL, and we measured the frequency shifts versus time for the complete system. And we introduced a water solution with suspended gold particles inside. And we could detect clearly peaks of in the order of 200 femtograms. So this was a nice demonstration of the working principle. So this concludes the first part of the talk, in which I talked about the fundamentals of the limits of resonators and the results that we obtained with our microfluidic devices. And then I would like to switch a little bit the topic, still in the resonant mass sensors, but I would like to discuss a little bit on control aspects, and specifically on what is the difference between measuring in open loop and closed loop, especially in terms of resolution. So to give an overview, as I've described before, we can have a closed loop system, such as the phase lock loop, which is a very flexible implementation, and we can implement with our Zurich Instruments lock-in. And this can give us a readout of the resonance frequency continuously over time, and from this we can calculate the Allen deviation. But actually, in open loop, as I said, this is not very practical scheme due to the drift effects, but we can also have a measurement of the resolution. And this is a very rather immediate way of determining the resolution, because we don't need to implement any feedback. We just interrogate the resonator, and we can obtain a value for the Allen deviation or the mass resolution. And how do we do that? Well, we can feed our displacement signal and our force signal into a lock-in, and the lock-in will give us a readout of the phase. And you will say, okay, but to measure the Allen deviation, we need actually frequency readings. But well, the frequency of a signal is just the time derivative of the phase. So we can use this fact and introduce this fact into the definition of the Allen deviation. And we can obtain an expression like this, which is detailed in this paper, in which we can determine the Allen deviation from phase data, only phase data. And you might think that this expression is a bit complicated, but it is not. It only uses like phase data points measured over time. This is the only information that you need to calculate this open loop Allen deviation. So to summarize a bit, we can determine the resolution in open loop, and this is a very immediate method. It's just an interrogation system. We don't need to implement any feedback. And we know that the result will be some characteristic of the resonator and also the measurement system that we are using to interrogate the resonator. So this information could be useful in practical scenarios, but we know that in practical scenarios we actually need a closed loop system to avoid these drift problems. So the obvious question is, are these two methods equivalent in terms of frequency resolution? And what I mean is, if we measure the Allen deviation in open loop, can that measurement give us information about what will happen in closed loop, or are the Allen deviation the same in both cases? So the most immediate way to find out is by just measuring the Allen deviation in open loop and closed loop for the same resonator. And we can see that this is not the case. Actually, for closed loop, we can see an increase of the Allen deviation, especially for long gate times. And well, specifically for gate times longer than the characteristic time of the resonator, which is just twice the quality factor divided by the resonance frequency. So to illustrate a little bit more why this open loop, closed loop distinction is very important, we can look at the literature. And in the last years, there has been some discussion on what is the influence of the quality factor on the Allen deviation when a resonator is at this ultimate thermomechanical limit that I described in the first part of the presentation. So there's this paper from Royo and colleagues and collaborators in Science that concluded that at this limit, the Allen deviation can be reduced if we actually reduce the quality factor of the resonator. Well, this is a very surprising condition because people usually try to increase the quality factor of resonators, right? And then just 1 year later, there was another paper from Demir and Hanai in IEEE sensors. And here the conclusion was that actually the ultimate limit for the Allen deviation is independent of the quality factor of the resonator. So these are different conditions for the same problem, different conclusions for the same problem. And the reason for this is that one group analyzed the response in open loop and the other one considered the closed loop behavior. So you can see here how important it is to have a clear view of what is open loop and closed loop in terms of Allen deviation. And in order to describe how we analyze this problem, I would like to introduce some definitions first. Well, we have a displacement signal for the resonator. We know that this signal in general can be noisy. And we can model this noise by this random variable here, this n of time. And we can take this approximation in which the noise of the signal is actually expressed as noise in the amplitude, called amplitude noise, and also some noise in the phase of the signal. And then we know that the frequency is the time derivative of the phase in a signal. So we can define also a frequency noise by just taking the time derivative of the phase noise. And then this is a time domain signal, but we can express it in the frequency domain by calculating its power spectral density. And this is what we call S omega, or power spectral density of the frequency noise of the signal. And why this is very important? It is because, well, the Allen deviation is fully determined by this frequency noise. So meaning that Allen deviation or frequency noise are just two ways of expressing the same thing in a signal. And we also know that, or we know how this frequency noise behaves when a system operates in open loop versus in closed loop, because this is called the Lisson's effect. And this is in general valid for any type of noise affecting the resonator or the measurement system. And the Lisson's effect is expressed by this equation, and this equation is plotted here. And we have that for certain frequencies above the characteristic frequency of the resonator, you have here, the frequency noise in closed loop is exactly the same as the frequency noise in open loop. But for frequencies smaller than that, the frequency noise in closed loop is bigger by this factor that you have here, which is frequency dependent. So this is why open loop and closed loop don't give the same Allen deviation. Then in order to tackle this problem, what we did was to translate this expression into the time domain, but undoing the Laplace transform or the Fourier transform. And we came out with this expression in which we can calculate the equivalent frequency perturbations of a resonator when it works in closed loop from the phase perturbations that we can measure just in open loop. And we see that in this relation, there is a proportional term, and there is also a derivative term. So based on this expression, we can propose a method to measure the perturbations in open loop, but from that inferring what is the Allen deviation in closed loop. And this is the method that I just described briefly here. So first, what we do is to interrogate the resonator in open loop. So as I said, this is very simple. We don't need to implement any closed loop, any feedback. And then we use our lock-in to obtain the phase over time. And then in the second step, we can translate these phase perturbations in open loop to the equivalent frequency perturbations in closed loop by just this expression. And then from that, we can calculate the Allen deviation by just taking the equivalent frequency perturbations in closed loop and using the Allen deviation formula. And to verify this method, well, we set a set of experiments with an AFM cantilever, like the one you can see here. And the cantilever was actuated with an external piezoelectric material. And then we measured the vibrations. And then we used Zurich Instrument digital lock-in in order to, well, first use it as a lock-in, but also as a phase lock loop. And then by doing this, well, we first measured the Allen deviation in closed loop versus gate time. And what is worth mentioning that, well, this Allen deviation is coming not just from the thermomechanical noise of the device, but in general from other sources of noise present in the vibrometer, especially. And as I said before, if we do the same measurement just in open loop, we will see that the result is quite different. And it's worth noting that in the literature, we can find a previous method in which they convert the open loop phase measurements into closed loop by just proportional relation. You can see that this method is actually valid for long gate times above the decay time of the resonator. But with our method that includes the proportional term, but also the derivative term, we can also, from the open loop, we can predict the closed loop Allen deviation. And this is the prediction from the method here in red. And you see that it agrees quite well with the directly measured closed loop Allen deviation. So I would like to summarize this talk and write some conclusions. We have demonstrated femtogram level resolutions with microfluidic cantilevers. And also we could compare the actual resolutions that we obtain with the ultimate limit that we would expect if the noise of the instrument is reduced. Also, we concluded that the closed loop operation is needed in most practical scenarios to avoid a drift and increasing the measurement range. And also we established the relation between the noise metrics, meaning the Allen deviation, observed in resonators when operating in open loop versus when they operate in closed loop. And thanks to that, yeah, we can develop a procedure to characterize the resolution in a very standard and immediate way, irrespective of the particular implementation of the feedback. So I would like to mention the publications that describe this work that I just presented. This one is coming soon in microfluidics and nanofluidics and contains the characterization of the microfluidic resonators. And the method to convert from open loop to closed loop is already published in this IEEE sensors paper. Then I would like to thank Mehdi Dariani for the nice measurements of the microfluidic resonators and its limits, and Murali Gatkesar, Parvo Talijani, and Peter Steineken for the nice contribution in the supervision and also in the nice discussions that we had. And finally, I would like to make an announcement. Well, as Kivanç mentioned, I just joined an assistant professor position, and yeah, we're already looking for talent. So we will have soon an open PhD position to work on piezoelectric micro machines, ultrasonic transducers. So these are devices that use piezoelectric materials in order to excite ultrasounds. So this has a lot of applications especially in medical measurements, in medical diagnostic procedures. So we have a very nice environment here until Delft and cutting edge fabrication and also characterization facilities. So if you are interested in this position, please contact me. And with this, I would like to thank you all and give the floor back to Kivanç.
Thanks, Tomas, for the great presentation. So what we learned today, we looked into the lock-in amplifiers and we seen that they actually foster information in a noisy environment to capture the information from the sensor. A modern NAC amplifier also then provides the toolset for sensor characterization. For example, in this example I mentioned, we can capture and track multiple eigenmodes, also Tomas mentioned. We also have the time and frequency domain characterization tools to enable to understand the sensor's behavior. And in addition, to analyze its impedance, an impedance analyzer based on the lock-in provides fast, precise, and accurate detection as well. So these concepts can be combined, as in this example, a phase lock loop and another PID for automatic gain control, and even further, more complicated schemes is possible. So in the end, sensor characterization and control all in one. With this, I like to conclude. Of course, challenge us. What is your next sensor development requirement? We are more than happy to discuss your new applications.